Hello, so today I wanted to talk about what the Z transform is and how exactly it is related to the Laplace transform. But first, let's say we have given an analog signal. For this example, I will choose an easier one. Let it be u of t equals e to the power of a times t. So and what we want to do now is turn our analog signal into a digital one by picking samples at a specific time rate. We call this a sample frequency, which is basically 1 times over our sample period. So we draw the time points where we pick our samples in our diagram. This is 1 times ts. 2 times ts, 3 times ts, and so on. So one could imagine this process as an electrical signal that is being connected to a switch that turns off and on at our frequency. So our sampled signal basically represents our original signal, where t equals k times our sample period. You can also write this sequence down fully by saying, okay, if k goes from 0 to infinity, then you say it's u when t is equal to 0, t is equal to ts, 2 times ts, and so on. However, we can also make use of the direct delta function, which is 1 if t equals 0 and 0 else. And we can also move it around by giving it an additional parameter so that it's 1 when t equals t0 and 0 else. Write our function down very elegantly into a series where our parameter is k and our signal samples are being represented by moved around direct delta functions. So from here now, we have our sampled version of our original signal. And now we take the Laplace transform of it. Now, given that the Laplace transform is a linear transformation, we can basically pull the transformation within our series and only do the transform on the time variant parts of the signal, which in our case would be only the direct delta functions. Because this part right here doesn't have t as a parameter anymore, it has k as a parameter. Over here, we have t. So the Laplace transform of the direct delta function would be defined as, we integrate from 0 to infinity, we plug in our function that we want to transform, and we integrate over our time domain. Now, if we imagine an integral to be an infinitesimal summation of all the values our function takes at specific times, and our function only having a value unequal to 0, only at t equals 0, we can write down our Laplace transform as e to the power of minus s t0. I know this is a very simplified way of thought, but For now, that'll do it, and we do not have to go further into it mathematically. Using this now, we can write down our Laplace transform of our sampled signal as the summation, the series of our sampled sequence times e to the power of s and not t0. Our t0 now would be k times ts. Now all that we gotta do is define z as e to the power of s times our sample period and replace it in our function. And now we have our z-transformed signal. If we get back to our original signal, and that was e to the power of a times t, and we plug in k times our sample period, that would be e to the power of minus a times ts times k, and we plug this into our function, so that e to the power of a times ts times k multiplied with z to the power of minus k. Now to make things easier, we will replace this term right here with c and write our series down as c divided by z to the power of k. And now one has to know that the infinite series of q to the power of k equals 1 divided by 1 minus q if q, the absolute value of q, is smaller than 1. If we apply this here, then our series comes down to 1 divided by z times z, and fully multiplied and formed, that would come down to z divided by z minus c. And this right here is the z transform of our original function. Now, if you look up tables online, this is also exactly what we have given. If we take into account that we defined z as e to the power of a times our samples period.